Hello friends, welcome back for another deep learning project where we will build a deep learning model which will denoise a noisy image, and that model will be built using the convolutional autoencoder architecture. So let's first understand what is convolutional autoencoder in the notepad. Then we will run this notebook to implement that convolutional autoencoder. So I am moving to notepad. So a convolutional autoencoder for image denoising is a type of DL model that learns to remove noise from images by capturing and reconstructing the underlying clean structures. I repeat, a convolutional autoencoder for image denoising is a type of DL model that learns to remove noise from images by capturing and reconstructing the underlying clean structures. Let me write so that you can understand it better. A convolutional autoencoder for image denoising is a type of DL or deep learning model that learns to remove noise from images by capturing and reconstructing the underlying clean structure. So the architecture comprises of two things. One is encoder and the second one is decoder. The encoder reduces the spatial dimensions of the input while extracting meaningful features. What the encoder does? The encoder reduces the spatial dimensions, that is nothing but height and width of image of the input. Here our input is image, while extracting meaningful features, and this returns a low dimensional latent representation that captures key image features. This returns a low dimensional latent representation that captures key image features. So how this encoder is built, that is what the question arises in our brain. So first we will have convolution layers which will extract spatial features. Then we will have batch normalization layer which will normalize the activation and speed up the training as well as stabilize the training. Then we will apply ReLU activation and finally we will have a pooling layer. In our case I have used average pooling layer. You can try max pooling layer also, and you should have to have this stride equals to 2 in conv layer and pooling layer. You should remember that. So I am explaining it again. The encoder reduces the height and width of an input image and extracts the important features using convolution layer, batch normalization layer and pooling layer with ReLU activation function. And the decoder reconstructs the denoised image from the compressed latent representation generated by the encoder. What the decoder does? The decoder reconstructs the denoised image from the compressed latent representation, that is nothing but the feature map generated by the encoder. And what it returns? It returns a denoised image, as our project is for denoising the image. So what it should return? It should return a denoised image. So it returns a denoised image with the same dimensions as the original input image. That's what we want. So again we will get the question how this decoder will be created. So in decoder we have layers like transposed convolution layer, which does up convolution or transposed convolution. So it comprises of transposed conv layers. The transposed convolution layer performs upsampling to increase spatial dimension. Then we will have batch normalization layer, and also ReLU activation layer. Then we will have skip connection, also called residual connection, and finally we will have a final convolution block with either activation sigmoid or softmax as per the requirement of our model. In our case we are working with black and white images, so we will be having a convolution with kernel size 1x1 and one filter and sigmoid activation function. So we will have a final conv layer with 1x1 kernel sigmoid activation function and one filter. This is what the architecture we will be using in our project to build our project. So after that, let's discuss some advantages and disadvantages before proceeding to the implementation of the model. So advantages: the convolutional autoencoder preserves spatial information, that means height and width. So the what it preserves? Spatial information. It preserves spatial information. Then as the convolutional autoencoder uses convolution layers, that's why it does efficient feature extraction. So we will find efficient feature extraction because of conv layers. The next, this architecture or convolutional autoencoder results a better noise removal. So better at noise removal. Then this architecture or model is not only working with one kind of noise type, but it can work with all kinds of noises types like Gaussian noise, short noise, etc. So we can write robust to different noise types, and as this is robust to different noise types, that's why we can use this for real-time application. Real world application can be used for real world application. These are some advantages of convolutional autoencoder architecture. Then similarly we have some disadvantages. Let's discuss what are those disadvantages. The first one is nothing but we will lose the fine details of the image because the encoder compresses the image into low dimensional latent space. I repeat, we will lose some fine details of the images because encoder compresses the image into low dimensional latent space. Loss of fine details because of encoder. Then the second disadvantage is that we will see over smoothing in the denoised output image. That is also a disadvantage. It returns over smoothed image. So these are some of the disadvantages of this architecture. If we fine tune this architecture, we will get the better model, but for the learning purpose we are not fine tuning the model, we are just discussing the convolutional autoencoder for image denoising purpose. So first of all, I am using accelerator as TPU. Environment preference is always use latest environment. Please make sure that you have this in your Kaggle notebook. So make sure you have accelerator TPU for accelerating your training. So yes, we have connected to the TPU. Let's run our model. So at first I am importing the required libraries like NumPy, Matplotlib, Tensorflow, Keras, and I am not using this MNIST dataset. Let's not import that. And from Keras I am importing layers. So let's run this. So it is taking some time. Wait a while. Yes, we got some warnings. Let's ignore that warnings. Warnings will come whenever you do projects. Go on ignoring that. Import of all required libraries is done successfully. Then we have to connect or build a strategy to use the TPU accelerator. So to build the strategy, first we have to create a resolver using this tf.distribute.cluster-resolver.tpu cluster resolver, and we have to pass local as the argument for TPU. Then we have to connect to the cluster with the resolver and initialize our TPU system with these two lines of code. Then we can create a strategy with the TPU strategy method passing the resolver. So let's run this and create this strategy. So TPU is initializing. You can see we have 8 cores in our system, TPU system. So successfully strategy is created. After that I'm using humans faces dataset for training my model. So you can find that in Kaggle. So first of all I have added this dataset to input section by clicking on this add input, and in that we have a subfolder humans, which I have copied the path by clicking over here, then having that path in the variable images path. You can do the same. Then I'm saving the path in the images path variable. After that, using the image dataset from directory method of Keras utilities, I'm generating the train dataset and validation dataset. For that I am passing the path of the folder, then validation split equal to 0.2, that is 20% of the images are reserved for validation purpose, and an argument subset equal to both, which returns both train dataset and validation dataset. Then an argument levels equal to none, so that no levels are extracted from the subfolder. Then seed equal to 1337, this is for regenerating the same train DS and val DS whenever we rerun this notebook. Then shuffle equal to false, so that the images won't be shuffled. then image size equal to 128 comma 128. That means I am resizing the images into the size of height 128 and width 128. Then having batch size of 160, so that I will be having 160 examples in each batch. So let's run and create both trained DS and well DS datasets. So it will take a few seconds. You can see we have 7219 image files. Among that, 5776 image files are reserved for training and remaining image files are reserved for validation. So let's check what is the shape of a image batch from the trained DS. So you can see we have 160 examples in each batch and 128 is the height of an image and 128 pixels is the width of an image, and we have 3 channels in each image. Then from these images I will create a noisy trained DS and noisy well DS by adding some noise to that image, so that we can give a noise image and a clean image to a model to train. For that, I am defining a scalar method and a noise method. The noise method will add the noise, while the scalar method will convert the image to grayscale, because we are working with only grayscale images. So in the scalar method I am passing a image, and first of all I am rescaling the image so that the values range between 0 and 1. Then I am converting the image to grayscale using RGB to grayscale method available in Tensorflow image module, and passing the image to that method, then returning the output. Then in noise method I am passing 2 arguments, one is image, another is noise factor. The default noise factor is 0.1, so that 0.1% noise will be added. Image equal to scalar, that means first we are doing this operations. After that we are generating some noise using the normal distribution with this shape, and we will have mean 0.0 and standard deviation equal to noise factor. And as we have d-type float 32 here, by rescaling the images we are having the same here. Then adding both noise and image so that a noisy image can be created, and clipping the value between 0.0 and 1.0 so that there should not be any image value or pixel value more than 1 and less than 0, and returning that noisy image. For both this function I am applying map method to both the datasets, and inside the map method I have lambda functions which will take out the image from the trained DS and well DS then apply the noise method to that images. And the second argument in the map method is number of parallel calls equal to tf.data.autotune. This argument allows TensorFlow to decide how many parallel threads to use when applying the map, which improves the CPU utilization. Then we have applied prefetch where tf.data.autotune is passed. This will preloads the next batch in the background while the model is training, reducing data loading bottlenecks. That is the purpose of having number of parallel calls and prefetch. So let's run this and convert our image to noisy images. Yes, successfully we have created noisy train DS and noisy validation DS. So after that, as our model requires a noisy image corresponding to a clean image, so we will zip both noisy image and train image. To zip that, we have a method zip in this dataset module of TensorFlow, and using that we will create a zipped dataset where we will get noisy train image and clean train image. Let's run this. After that, as the noisy train images are converted to grayscale, but the train images are not converted to grayscale. That's why I am reapplying the map method to ds train and ds val to convert the clean image to grayscale, doing the same which I applied to train ds. So it will convert clean images to grayscale. So let's run this. After that, I am checking the shape of noisy images batch and clean images batch. Let's run this. You can see we have 160 images in a batch of noisy images and 160 images in a batch of clean images, and we have height 128 in both noisy and clean. Similarly, we have 128 width in both noisy and clean, as well as we have channels equal to 1 in both noisy and clean images. After that, I am plotting noisy image with respect to a clean image. So let's plot that. To plot, I am using matplotlib, and this is the basic code. I hope you will understand and I don't need to explain this. So you can see this is the noisy image and this is the clean image, and this is the noisy image and this is the clean image, and here it is the noisy image and this is the clean image or normal image. I have mentioned normal, but it is clean image. Similarly, it is a noisy image and it is a clean image. And now we will implement our model. So in our model we have one encoder and decoder. The encoder part is this, the convolution block, and the decoder part is this up convolution block. So in encoder we have inputs, number of filters, and the strides. So in encoder part we will have a convolution layer, I already told, and a batch normalization layer and a average pooling layer with ReLU activation function that I already explained when I was explaining about the architecture. So let's run this, and we will have 3 cross 3 kernel and SAM padding. Then in up convolution block we will be passing inputs, filters, and residual. As I explained about that skip connections, for skip connection we will be passing the residual, and strides equal to 2. So here we will have a transposed convolution layer with kernels 3 cross 3 and padding SAM with ReLU activation function, then a normalization layer, then a residual connection with this add layer, then again a transposed convolution layer and a batch normalization layer at final. So let's run this. So our model is of a encoder and a decoder, but we will use the convolution block or encoding block several times and also the decoding blocks several times. So here you can see we have a input layer with SEP 128 to 128 to 1, as we will be passing grayscale images. Then for the first convolution block we have strides equals to 1, because when we will recreate the final image we will have the stride equal to 1, and here the number of filters equal to 128 and the inputs what is here available. Then we will have a convolution block with 256 filters. Then we will be having a convolution layer with 512 filters and a batch normalization layer. Here we are not applying the average pooling, that's why I have not used the convolution block. Are you clear? I will repeat it again. Here we have not used the average pooling layer, that's why I have not used the convolution block. Now in transposed convolution, that is up convolution block, x3 is the input, that is this is the input, and we have 256 filters, and x2 is our residual. So you can see the x2 has the number of filters equal to 256, that's why when the filters equal to 256 we are passing x2. Is it okay? Then we have another up convolution block with x4 as input, that is the output of the last up convolution block, then 128 number of filters. Next one is the residual, that is this one. Then we will have a final convolution layer with one filter, 1 cross 1 kernel, and stride equal to 1 cross 1, same padding, and also sigmoid activation that I already explained you in the explanation of architecture section. Then we will be building the functional model with these inputs and outputs, and we will return the model. So let's run this. After that, I am using binary cross entropy as loss and Adam as optimizer, and to use the accelerator, that is TPU, you have to write or create the model under the strategy.scope, that is TPU strategy, and also you have to compile the model under the strategy. So let's compile it. Model is compiling. Let's go for model summary. Here I want to show you one thing, that's why I have used model.summary. Our input layer has image size 128, 128, 1, and our output also has 128, 128, 1. That means our model will take the input shape of 128, 128, 1, and also produce the image of shape of same shape as the input. And before training the model with noisy and clean dataset, I am training the model with clean dataset so that the model learns to create the same image as given to it. For that, I am extracting the clean images from the train DS and validation DS. That's what I have done here, and saving that in the variable train DS original and val DS original respectively. With that, I am training the model for the first time so that the model learns to recreate the image as it is. Let's run this. I have 50 epochs, and do not be worried about the time. I will increase the speed. After the 50th epoch with original image train DS and validation DS, we have a training loss of 0.4912 and validation loss of 0.5283. So let's see whether our model is able to create the original image as it is or not. For that, I am iterating over the validation dataset original and taking one batch out of it and separating both noisy images and clean images, and predicting the denoised images, that is nothing but, here I have mentioned denoised images, but recreating the images. Let's not change the code, and then iterating from 0 to 9 with step value 3, and selecting the subplot and showing the first image, the original image, and the second image is also original image, and the third image is the recreated image. Let's run this and check what is the accuracy of recreating the image. So we got some warnings. Okay, here you can see these two are original image and this is the recreated image. So our model is able to create good quality recreated image. So okay, nice. Let's move on and train the same model with a noisy image as X input and a denoised image as Y input, and check whether the model is able to denoise the noisy image or not. So for that I am using DS train that contains both noisy and clean images. Similarly DS val, which contains both noisy and clean images, and also I have a checkpoint which saves the checkpoints with monitoring the validation loss with minimum values. Let's run this and train out the model. The first epoch is started. After the 50th epoch, we got a training loss of 0.4929 and validation loss of 0.5310. So let's do some inference. Change the noisy image to denoised image with our model. So for that I am again doing the same, repeating the code but changing only the dataset and the titles, that is noisy, the original image and the denoised image. Let's see how the model predicts. So here you can see this is the noisy image, this is the original image, and see the model is recreated a denoised image is somewhat good enough. And here you can see this is the noisy image and it is a clean image and the denoised image. Wow, the model is doing a good job. And here you can see the noisy one, the clean one and the denoised one. Wow. So after that let's evaluate the model with validation dataset. So we are getting a loss of 0.531 and let's load the best model from all the checkpoints we have with us. So to load that, using load model and evaluating the loaded model. So let's run this. So we will see some improvement over this loss because we will get the best model out of all checkpoints. See, we got 0.5172. Wow, so minute change, what a great change. Then we will be checking how the image becomes denoised comparatively to the previous model. Let's see how much denoise is done by this loaded model. You can see the loaded model is somewhat better than the original model. Now let's save the loaded model because it is the best model. So we have saved our model, and I want to say one thing, that I am not going to develop a user interface for this project. You can use my code and my model which I have developed, and you can get it in the description box. I will provide you the link of this notebook, don't worry about that. And this is the model which I have created, and these are the checkpoints. You can download it by clicking on three dots and clicking on this button. So thank you for watching me patiently. Thank you very much.